My name's Morton. Today I'm going to talk about Cassandra codebase. Obviously it's a quite complex codebase, it solves complicated problems, so we're not going to dive into in great detail. What I'm going to do instead is pull out some of the more important classes and point to some of the places where exceptions happen that you might get as a client or timeouts are raised. A little bit about me before we get started. I'm a freelance Cassandra consultant. I'm based in Wellington, down in New Zealand, and I'm a committer on the Apache project. We're going to start by talking about the architecture, and then we're going to dive into the code base. Architecture-wise, we can draw a pretty simple diagram. There's some clients, they connect to APIs. Those APIs talk to some software components that we can call cluster aware. They in turn talk to software components that are cluster aware, which read and write from disk. When we put this stack together in a cluster, as you'd expect, the cluster aware components talk to each other. The cluster unaware components continue just to do their thing, reading and writing from disk, without worrying about the other nodes. But we can put some better labels on this diagram. Cassandra is a Dynamo-based system. So let's call our cluster aware components the Dynamo layer. And let's call our cluster unaware components the database layer. Cassandra is just a fast log-structured storage engine with this Dynamo layer on top of it. The database components take things from memory, put them on disk, take things from disk, put them in memory. The Dynamo layer collects that memory on the various machines, brings it together on the coordinator. That's where we take care of eventual consistency and all those guarantees, make it available to the API, and it gets sent back to your client. So we can expand our overview today. We're going to talk about an API layer, a Dynamo layer, and then a database layer. We break the API layer up into two, transports and services. We use Thrift as a transport. And if you do nothing, your API call starts in the custom T thread pool server. In these slides where I have OAC, I'm talking about a Java package in the code base, org Apache Cassandra Thrift, custom T thread pool server. This guy uses a thread pool that has one thread per client connection. That thread stays with the client connection for the life of the connection. At the end of it, does some cleanup, and then goes on to process another client. You might also find in the code base a custom T non-blocking server. That's an older deprecated server. What you will find though is the custom T HA server. You choose the server type using the RPC server type YAML configuration. The default sync is the custom T thread pool server. HSHA chooses the HSHA one. The difference is HSHA uses a thread pool, and each thread processes one request from a client and then goes on to look for another request to process. It's a bit more efficient in terms of the number of threads that are used. And that's the Thrift, and it's pretty simple because a lot of that code is Thrift code, and we don't want to talk about that today. Native binary is new in Cassandra 1.2. In fact, it's labeled beta. It uses Netty under the hood. Disabled by default, you enable it using start native transport in the YAML. You can run both Thrift and native binary. They use two different ports. They happily coexist. We can dig into this guy a little bit further. It starts in our server class in the transport package, in the run function, build the execution handler. This is our thread pool. The thread processes one request from a client, then goes on to find another request from a different client, perhaps to process. So to do that, it uses NIO server sockets under the covers, and it sets up this thing in Netty that we call the server pipeline. This has a series of stages that your request goes through. So there's frame encoding and decoding, frame compression and decompression, message encoding and decoding, up to a stage called the dispatcher, which is where your request actually runs. Our dispatcher is in a class called transport message dispatcher. It's got a pretty simple message received function on it. This gets called with a message. It gets our server connection and validates that we expect to receive this message for our current state. If we're already authenticated, we don't expect to be given credentials. We take the request and we execute it. That gives us a response that we want to send back to the client. Before we do that though, we get that server connection again and check to see if we want to make a state transition. So do we now move this server connection into an authenticated mode because we've actually got the credentials and everything's good? The messages in that native binary transport are described in a human-readable document that's in the source tree. You can go and have a look and get a really good idea of what this protocol is talking about. Onto the services layer now. JMX, you should all be familiar with JMX. You need to know how to use this to admin your servers. The management beans that it expose are spread around the code base, but they all implement interfaces that end with nbean, so they're pretty easy to find. The interfaces themselves all have pretty good documentation on them, so you can go and look that up, find out what they're doing. They're implemented in a really sensible way as well. There's an interface called storage proxy nbean. It's implemented on the storage proxy class, and it's exposed in JMX as org Apache Cassandra storage proxy. Pretty easy to track those down. Onto Thrift at the service layer. This is our RPC interface, and it's implemented on the org Apache Cassandra Thrift Cassandra server class. This implements the entire Thrift interface, does the sorts of things you would expect it to do, has access control, input validation, and it maps from the Thrift types to our internal types and back again because we don't use Thrift internally. That Thrift interface is in an IDL and interface definition language file. It's not a very human-readable document, but you can go and have a look, and there's some few comments in there, and you can get a bit of an idea of all the functions that are available on that Thrift interface. Let's take a look at probably one of the more popular calls on it, get slice. This is where we want to get some named columns or a slice range of columns for one particular row. This code example is from 2.0. So the first thing it does is it sets up request tracing, if that's enabled on this request. It gets the client state. We have client state for both Thrift and native binary connections. And on that client state, we have the key space that you're working in, and we have your username if you've authenticated. Use that to do our access control. And because this is a pretty common function, now we've got to go through a few abstractions here to complete our read. We go over to multi-get slice internal. This is where we validate your Thrift request. Did you ask us to return -1 rows? Something like that. And then we create an internal representation of your request in an object called a read command. This is something we'll execute later on to get your results. We hand that over to get slice, and here we start to see a blend from the API layer into the internal structures. This takes the internal read command and it returns Thrift types. It has a function called Thriftify, that's where it does that. To get the data that it is going to return back, it hands the read command over to this read column families function, which takes the read command and returns our internal representation of its result, which is called a column family. And it does that by handing the read command down to a class called the storage proxy. We'll see this guy later, but the storage proxy lives in the Dynamo layer. This is the end of your API call if you came in through Thrift. Over to CQL3 now. The equivalent to the Cassandra server is pretty much the query processor. This guy prepares and executes CQL3 statements. It's used by both Thrift and native binary. If you call execute CQL3, you come into the Cassandra server and jump over here for the execution. Has the access control and input validation that you'd expect, and it returns transport messages instead of Thrift messages. So when this is called from Thrift, there's a little bit of extra work to Thriftify that result. CQL3 itself is described in an Antler grammar. Again, this is not a human readable document. It's designed for the Antler compilers, but you can have a look in there and get a pretty good idea of the nature and the structure of CQL3. The statements in that language are processed in a two-phase approach. First, we create these things called parse statements. These are created by the Antler compiler, and they're essentially a representation of what you've sent to the server. Has some extra things on there for tracking bound terms if you're using prepared statements. Has a prepare function on it, which then creates something we can execute. It's called a CQL statement. These guys have access control and input validation because we need to check that you're allowed to delete or insert or read. And they have an execute function when we want to run it. If you have a look at the parameters there, you can get a feel for this. The consistency level, that's a parameter. Query state and variables that we want to run. These are all parameters. If this is a prepared statement, pass those guys in, and away we go. So obviously, the most popular and most complicated CQL statement is the select statement. It has an inner class which implements the parse statement, has a lot of logic in there to understand what you're actually saying in the select clause, and it creates a select statement for us, which in its execute implementation creates a read command. These are the same objects, the same classes that the Cassandra server uses, and it passes these down to the storage proxy, and this is the same storage proxy that the Cassandra server uses. So your API call comes into Cassandra and either goes into the message dispatcher or the custom T-thread pool server, comes to the query processor or the Cassandra server, and then onto the query processor. At that point there, for a read, we create read commands, and we hand them down to the storage proxy, and we start to transition into the area of the code that I call the Dynamo layer, where we're having to deal with the fact that we're running in a cluster. There's a number of packages that I could conclude in the Dynamo layer here that we won't get to today for time constraints. DHT package, it's the distributed hash tree, that contains the partitioner and the tokens. The GMS package contains the gossip implementation. The locator package contains the partitioner, contains the replication strategy and the snitch. And the stream package contains the logic that we have for streaming files between nodes during repair and bootstrap. Let's dig into the service package though. Storage proxy, we saw this guy before. This guy's the workhorse of the Dynamo layer. It's the entry point for all of our cluster-wide storage operations. Reading and writing all goes through here. It does the sorts of things you'd expect. It selects endpoints, it checks if there's consistency level nodes available, it sends messages to stages. These are the stages in the staged event-driven architecture that Cassandra uses. We'll see more about those shortly. It sits around and waits for a response in a very efficient way, handles hints if we got a timeout or something like that, and then returns the result back to the API layer so it can go back to your client. There's another important class in here. That's the storage service. This guy's a wrapper for a lot of functionality that's implemented elsewhere. Everything to do with tracking the ring state, starting and stopping ring membership, mapping between nodes and tokens and nodes so that we know how to find your replicas for reads and writes. So the storage proxy comes along and it uses the storage service and it works out, we're going to do a read and we're going to send a request off to 3 other nodes, say, to do this read. Hopefully, we'll get back a bunch of results, 2 or 3 of them, and we need a way to resolve any differences. And that's handled by objects that implement the iResponse resolver interface. Pretty simple interface here. We call preprocess when we get a message from another node. Once we've got enough of those, we call resolve, and that will either give us the response we want to send back to the client or throw an exception. The row digest resolver is used the first time we run the read. This is where we ask one node to give us the data that we want to return to the user, and the other nodes to give us a digest of the data that they would send. In the resolve implementation, it creates a digest of the data response, compares that to the other digests. If they don't match, it throws a digest mismatch exception. If they do match, it returns the data, and we send that back to you. If they don't match, the storage proxy will run the read for a second time. And this time it asks all the nodes that are involved to return their data. So it uses the row data resolver. This guy's a little bit more complicated. It works out the final result that we would send back to the client using those timestamps to get the correct value. And then it works out the deltas between all of the replicas that participated in this request. It creates mutations to fix those deltas. It sends them one way to the remote replica. It doesn't wait for a response, and it returns back that correct result that it calculated. And we hand that back to the client without waiting for the remote replicas to fix their inconsistency. If you're doing a range scan, we have to use the range slice response resolver. A bit more complicated again. In a range scan, your replicas can return different numbers of rows. So this guy has to handle the fact that one node could return 5 and another node could return 10 rows. So that's great on the read path. Well, obviously, we don't use that on the write path. We do, however, have a commonality between the two. It's called a response handler or a callback. This is an object that implements the async callback interface, comes from the networking package, and it's a way for the messaging package, to deliver a message to an object that understands your request. This object is in charge of making sure that your request gets completed. Simple interface, we call response, we hand over the message. It's implemented in a class called read callback, and there's other ones for writes as you'd expect, but the get function on here is handy. We call this when we want to get the response from your request. It waits on a condition. If that condition is not set before RPC timeout occurs, we finish waiting and we raise an exception that says read timeout. This read timeout gets turned into a timed out exception that gets thrown back to you, the client. The condition is set once we've received enough responses. So that happens in our implementation of response on the async callback interface. So what we're waiting for is consistency level nodes to come back. So if you're doing a quorum at RF3, we're waiting for 2 nodes, and the data response. So the one node that we asked to give us data. When we get those, the condition is set, we pass through, then we use the resolver to get the result we want to send back to the client. This all comes together in the storage proxy in a function called fetch rows. This guy gets a list of read commands. It iterates through them a couple of times. In the first pass, it goes through and creates a list, and for each one, it creates a list of the sorted endpoints that we want to send this read to. This takes into consideration proximity and the consistency level. It constructs a row digest resolver because this is the first time we're doing this read. It uses that and some information about the consistency level and the endpoints to construct the read callback. It uses the read command to create messages so we can send those read commands to other replicas, and passes those messages and the read callback to the messaging service, send RR function, send request response. So the messaging service now is going to send those messages to the remote replicas. When it gets a response, it's going to deliver them into our read callback object. And we saw that with the async callback interface and the implementation of get. After we've done this for all of these read commands, we iterate through all the read callbacks that we created and we call get. Remember that get is blocking. That could throw an exception. The digest mismatch means we run it again. And the read timeout means we have to throw a timed out exception back to you guys. In the Dynamo layer, the network package has both a protocol and a transport. We're just going to talk about the protocol. It talks about verbs, request and response verbs. The messaging service doesn't know how to process the verbs though. It delivers them to objects that implement iVerb handler. Just having an object isn't enough, we need a thread. So we map those message verbs onto stages, onto the thread pool stages. So this comes together in the messaging service receive function. We take our message and we wrap it in a message delivery task. This is just a runnable. We take the message type and we use that to get the thread pool we want this runnable to go on. And we drop the runnable into the thread pool, and we go back and look for the next set of bytes to come off the socket. This is running on the thread that's just reading from a socket for one particular node. In the message delivery task, we look at the time that this object was constructed, and if it was longer than RPC timeout, we drop the message. And it's a droppable type message, we drop it. So when you see dropped messages in the logs, they come from here. If everything works, we get the verb handler object, we call that, and we pass over the message, and we're now processing your read in the read stage on a remote node. Quickly now onto the database layer. The thing that you think of, the concurrent package just maps stage names to thread pool executors. These are the things you see in node tool TP stats. In the database package, the thing that you think of as your key space is implemented in an object called table. We have one instance of these for each table. We call open to get that instance all the time. Has a function called get column family store because the thing that you think of as your column family or table is implemented in a class called column family store. This has the top level functions that we use for doing reads and write, get row and apply. over to our column family store. We have a top-level function here to do reads, get column family. We have an apply function. I'll skip down here because I'm running a little late. We have iSorted columns. This is the guy that contains all of your column objects. We have 3 implementations. The array-backed sorted columns is thread unsafe and used on the read path. The atomic sorted columns has isolated updates. It's used by the mem table. And the tree map backed sorted columns is a thread safe structure we use in multiple places. So I have to just skip forward a little bit. So in summary here, we come in through the API into a couple of different ways, but we always come down to creating read commands or mutation commands, dropping those into the storage proxy in the Dynamo layer. That uses response resolvers and async callback objects and the messaging service to transport this read command into the correct thread pool on the current node or on a remote node. That goes through the table in the column family store and the disk atom filters, which we didn't look at, which is where all the reads happen. It's just a series of iterators that pull stuff off disk. And we roll that back up and we get the result back out to you and the client. So unfortunately, that's all I have time for today. So I think I'm even too late for questions. Is that correct? So sorry that went a bit fast, but we started a bit late.